Okay, jumping into lesson 1.2. This is part 3. Probably like day 5 at this point, but it's one of those, there's a lot to it, right? Is there any way I could have done this all at once and then have you do one big homework over it? I could have, but that would be horrible. So, A and B, a long homework assignment, and B, there'd be a lot in it. You'd have to go back and remember. So, okay, so our first topic today is about even and odd functions and symmetry. So, we're going to talk about whether a function is what we call even or odd or neither. Okay, so if you look at some definitions here, functions that have or that are considered even. Okay, if a function is what we are is called even. First of all, we can physically identify it because it has symmetry across the y-axis. So it has that vertical symmetry. So that's how you can, if you're looking at a graph, you can physically identify it that it is even if it has symmetry across the y-axis. Algebraically, if a function is even, then this is true. So if we only have the equation to look at, we don't have the graph, if f of x is equal to f of negative x. And I will show you what that means. I will demonstrate. But the idea is if the original function is equal to the same thing when you put in negative x instead of x. If those are still equal, it is even. Functions that are considered odd. Now notice, I know you were hoping or expecting me to say symmetry across the x-axis, but I'm not. It's symmetry across the origin. I just realized, should I turn these lights down to eliminate some glare?
Well, that was hard to check the answer keys.
I wish you guys would have said something sooner. Sorry, I forget sometimes.
It's okay.
Does that help a little bit?
Yeah.
Okay. Symmetry across the origin. Now, symmetry across the origin is kind of like a diagonal symmetry in a way. The easiest thing I can think of, and again, I'll show you an example, but if it's symmetry across the origin, if you reflect it twice, once across the x-axis and then a second time across the y-axis, and your original matches your new one, that's symmetry across the origin. If you reflect it across both axes, the order wouldn't matter. But if you take your original, reflect it across the x or y, and then take that image and reflect it across the other axis, that is symmetry across the origin.
So you're saying wherever each of the functions would meet up at as the origin would be?
No. It'll be in a different quadrant. It'll end up in a diagonal quadrant.
Oh, you're
so again, I'll show you an example.
I get what you're saying.
Okay. Now, that's if you have graphic. Algebraic. If it's algebraically, if you just have the equation to look at, f of negative x, so when you plug a negative in for x, or negative x in for x, is equal to negative f of x, which means when you multiply the whole function by a negative. If those two are equal, it is odd or has origin symmetry. Okay? Like when I talked about asymptotes. There is a benefit for being able to look at an equation and answer it. There's a benefit for being able to look at the graph and answering it. Your best bet is to be able to do both and work together with them. Because in some situations, you want to be able to look at the equations. In others, you want to be able to look at the graph. Does that make sense? Okay. So, the examples we're looking at. Tell whether the functions are odd or even, odd or neither. Also determine their symmetry. Well, once you know whether it's even or odd, you'll know the symmetry. So look at example A. Now, we could graph this, but I'm not going to right now. Honestly, some of you already know what this graph looks like without graphing it. Okay, that is very possible. Okay, now, here's what I want to, okay, let me address it. We didn't graph it on the calculator. We don't need to, technically. X squared minus 3. X squared is the parabola. Minus 3? Down 3. So, okay, let's go ahead and talk about this way. What kind of symmetry does a parabola have?
Symmetry on the y.
Symmetry on the y-axis? Because that y-axis divides in half, correct? So if it's symmetry on the y-axis divides in half, what's that saying about this problem already?
Even.
This is going to be even. Easy to do if you have a good graph to look at, right? Or if you know what the graph is. Now, I want to prove this to you algebraically. Okay, so algebraically, first of all, we already have f of x equals x squared minus 3. First thing I want to do is I want to find f of negative x. So f of negative x says I take f of x, and every place I see an x, I'm going to replace it with negative x. So it's currently x squared. That means instead of x squared, I'm going to do negative x to the second. I'm putting negative x in for x, so I'm using parentheses, minus 3. Well, do the math here. What happens when you take negative x and square it? Anytime you square negative, you're back to a positive, aren't you? And then the minus 3, does it change? No. So I now have x squared minus 3. What do you notice here? F of x was x squared minus 3 and f of negative x. These two are equal. If f of x, the original, equals f of negative x, what do my rules say up above? Then it's even. Now, we technically already knew that, but there's your algebraic proof of how that works. Okay? The graphic proof was the fact that we visualized that this is a parabola shifted down 3, so it is symmetric across the y-axis. Because the other thing it says is determine their symmetry. So I'm going to say symmetric across y-axis.
So why do you think that x squared negative x squared?
Because you had to set that.
Well, we had to find f of negative x, which means anytime I see an x in the original equation, I substitute in negative x. So x squared says you take whatever you're substituting in and you square it. I was substituting in negative x, so I took negative x and I squared it. That's what the rule tells me to do. Does that answer the question? Maybe, maybe not. Okay. B. Okay, let's talk about the mental part of this real quick. Do you know what this equation looks like?
Yeah.
There's an x squared as the highest power, so again, it's going to be a parabola. Although, where is this parabola? You probably don't know that off the top of your head. Because there's, I mean, that minus 2x, this is going to be moved. This is going to be moved not just up and down, but also sideways. Okay, so if we factored it, we could find zeros. I'm not going there right now. The point is, it is still a parabola, but where it lands will depend what kind of symmetry it has. Okay, so we'll look at the graph here in a moment. So let's do this algebraically. First thing I'm going to find is g of negative x. I'm saying g of negative x just because they gave me g this time. Okay. So every place I see an x, I'm going to replace it with a negative. So the negative of x squared minus 2 times negative x minus 2. Now I'm going to clean that up, but that's just me showing how I plug the negative x in. When I clean this up, what happens when you have negative x and you square it? Positive x squared. What's minus x times negative x? Or minus 2 times negative x? Plus 2x, and then minus 2.
It's not equal.
Okay, so this right here Do g of x and g of negative x equal each other?
No.
No. So that tells me right now that this is not even. Okay? That's what I know at this point. Because those two did not work out to be identical. I know there's only one little sign difference, but it's not identical, so this is not even. Got it?
Okay, so which one
Now.
Which one will we plug into the graph?
The graph would always be the original.
Okay, that's my fault.
Okay, now, in order to figure out if this has origin symmetry, we already know g of negative x. We also have to know negative g of x. Negative g of x says I take the original g of x function and multiply it all by a negative. So like distribute a negative. So I'm going to write it as the negative of x squared minus 2x minus 2. That's how I'm kind of showing the initial step. I'm going to take that negative, multiply it into everything. Which does what? It takes every sign and flips it. So it's now negative x squared plus 2x plus 2.
Which is also
Now, if it is odd, negative g of x and g of negative x equal. What do you know? They don't equal. So this is not odd at this point, thus it is neither.
So
I just spelled neither wrong. It's not even a difficult word, really, and I'm going to spell it wrong. At least I caught myself.
Didn't say that.
It's okay. I spelled England wrong the other day in history, and that's my last name.
Okay, so this is an example of neither. If I pull this up on the graph real quick, okay, it's definitely not even because it's definitely not symmetric across the y-axis. The origin, it's not going to work, okay? If we start flipping that upside down and then left to right, it just doesn't work. I will show you one on Monday that has the origin symmetry that is odd. So, it is 10:13. Bell's going to ring on me here shortly, right? I've got my timing right. So, I would really have liked to have gotten that third example done, but it's not happening. Monday, we will pick up where we left off in the notes. That means page 95, 48 through 66 evens will be due on Tuesday. So I'll have to go back and review this with you anyways to remind you. So you have no actual homework tonight. E-learning tomorrow. Do that front page of lesson 1-3 notes. You don't have to flip to the back of lesson 1-3. You don't have to do that part. Just do your best to fill in those notes. In class, you got it? Virtual, you guys okay with what I said?
Fridays.
Okay. Good deal, guys. Everyone have a good e-learning day, and I will see you on Monday.